In few consecutive lecture, we shall discuss the electric dipole. Today, we shall describe the field potential and field as produced by dipole. It is found in reality that there are systems which are as a whole charge neutral, but they produces field in its neighborhood, and it also interacts with a similar element. As for example, two water molecules, they are as a whole electrically neutral, and two water molecule interacts electrostatically. The simplest system of this category is an electric dipole. It is an electrostatic system. That means the charges at rest. Electric dipole is comprised of two equal and opposite point charges, minus q and plus q. They are separated by a distance 2s. If we want to find out field at a distance r from the center of the dipole, then r is much greater than s. This is the definition of dipole. That is, the separation between the two charges is small compared to the distances involved in the discussion. And for a point dipole or an ideal dipole, 2s goes to 0. At the same time, q increases, so that the product P is equal to Q times their charge separation is a finite quantity. This is called a point dipole. Our objective is to find out field potential and field at point P. The point P is at a distance r away from the center of the dipole. We consider the plane defined by AB and OP to lie in the z is equal to 0 plane. So the geometry is in xy plane, and for convenience we represent the coordinate of the point as r theta. In that sense, the coordinate of B point is S0, and that of this is S pi, and this is the 0, 0 pi. First time we shall calculate the potential at P due to this dipole. So potential at electrostatic potential at R, which is actually R theta, is the potential at P due to algebraic sum of the potential at P produced by Q at A and that at P produced by plus Q at B. So it is K Q BP minus SI factor, where K is the SI factor when the charges are placed in vacuum. We take KQ common, and if we write it in terms of vector notation, this is R minus S modulus R plus S modulus. Now since R is much greater than S, this is the by assumption definition of a dipole. So we could expand these two in binomial series in powers of S by R, and since S by R is very small, it is sufficient to keep up to first order term. From this term, 1 by R 1 plus S by R cos theta plus this is the continuation coming from this term, minus 1 by R 1 minus S upon R cos theta plus S upon R whole square 3 cos square theta minus 1. Now you see that these two terms gets cancelled. Similarly, these two survives and adds up. So this contribution, entire contribution is come from where, and as there is an approximation, we put an approximation sign over here. Now the next step is KQ upon R, and this is twice S cos theta by R. Again, the next oral term that will contribute is S by R to the power cube, which is very small since S by R is very small. So we have neglected that term, and again there is an approximation sign. So there is approximation in coming from here to there, and there is another approximation here because we have neglected S by R to the power cube and other terms. This can be written as, in terms of P, this can be written as Kp cos theta by R square. But P is the electric dipole moment. It is found that in the discussion involving dipoles, the term Q and S never comes separately. They always come together. That's why we define. It is legitimate to define the quantity P, the dipole moment, and the dipole moment vector is by convention directed from negative charge to the positive charge. In that sense, cos theta is the angle between P and R. Keeping this in mind, we can write it K P dot R upon R cube as the potential at point P due to a dipole. So the potential at point P, which is at a distance R from the center of the dipole, is given by this. Another thing, if we think of the potential from the point of view of multiple expansion, this is a system with total charge 0. So there should be no monopole term, and if we expand the potential in multiple expansion, the first non-vanishing term is the dipole term, which is this. Then the quadrupole term will be 0 for this particular system, and then the octupole part will come. So this is all about the potentials. Note that the potential varies as 1 by R square, unlike the potential due to a point charge, which varies as 1 by R. Now we come to calculation of field. Field can be calculated in different ways. One way of calculating field, the radial and cross-radial components of field can be obtained by this. Now the field due to this dipole is minus gradient of potential. In polar coordinates, this comes out to be minus r cap del r plus theta cap by r w theta operating on phi e of r theta. This will give you r cap er plus theta cap e theta. From you can find out, one can find out the radial and cross radial components of electric field. That has been already done in connection with Coulomb's law. Now we shall go to another way of deriving the field. Homework. Note the homework. Find ER and E theta, and also the equation of field lines Now we come to the calculation of field in a different way. In this way, we shall, in our calculation, we shall use the field. For potential, we shall use this expression and find out the field. So the field will be let me just copy the parts, then I will erase the next. P dot R by R cube. This is minus K times this is the figure. Now let me calculate the term 1I1. First come to this term. Calculation of grad of P dot R. If we do it in Cartesian coordinates, this is I cap del del x plus j cap del del y plus k cap del del z. This is the operator nabla times this part xpx plus ypy zpz, where px, py, pz are the Cartesian components of the dipole moment. This dipole moment, when resolved in x, y, z component, these are the components. If we assume that the dipole is a fixed dipole, in that sense the vector p is a constant vector, that is px, py, pz, they are all constant. So when this operates on this, we will get only I cap px. When del del x operates on that, it is 0, and on this is 0. So this is the I cap px. When del del y operates on this is 0, and when it operates on it is y j cap py, and this is 0. Similarly, so this is altogether vector p. So this term has been evaluated, and this is vector p. Let me remark it as vector p, and this part has been evaluated, and it is vector p. Now let me calculate this part. Another way one can calculate this in another way. Let me also show the calculation. Alternatively, consider the back-car rule. A cross B cross C. This is the vector total product. Or in the case of three vector fields A, B, C, one can write B over here or over here. Similarly, C can be written here or here. We use this vector identity for the evaluation of this term. We recognize this with B, this is with B, this term with B with A, and this with C. We identify them. So the left hand side is nabla. For B we write nabla, and for A we write P, and for C we write R. So on the right hand side, what we will get? A, for A we write P cross curl of R, plus, here comes the trick, C is equal to R. So it should be written, usually we write at R dot the cross product A is P dot nabla. But this is an operator. It should operate on R. So we write R on the right. Instead of a constant vector P, if we have two vector variable vector, then there will be two more terms. Here the nabla operates only on R. There will be similar terms when nabla operates on the first vector. This is another way of arriving at the vector identity. You know that this is 0 and this simply gives you P. So the first term has been over, calculation of first term is over. Now come to this term. Now you know that this term, calculation of gradient of 1 by r cube. In general, we know that this is equal to 3r upon r to the power of 5. But this relation is valid so long as r is not equal to 0. At r is equal to 0, this term has a singularity. Or this is not the value at r is equal to 0. So we write it as, but altogether it will be a vector along r cap. So we write it as g of r times r cap. That is to say, g of r is obtained by dotting this with r cap. This is g of r. Our aim is to find out g of r, which is valid for r is equal to 0 as well as for not 0. R, note that r is equal to 0 is this point. That is when one wants to find out the field right at the midpoint between the two dipoles. One can calculate it. So we recall a vector identity involving delta function is that delta of r is equal to divergence of vector r by r cube. This we write it as 1 by r cube divergence of r, thus r dot gradient of 1 by r cube. Note that the vector identity that I have made use of is phi times a, divergence of phi times a is equal to phi times divergence of a plus grad phi dot a. This is the vector identity that I have made use of. Now this term is 3. So this is 3 upon r cube. And this term, as per our definition, this is g of r. This. So this is equal to 3 by r cube plus r times g of r. So g of r is obtained by dividing both the sides. Well, let me write g of r. When this is taken on the other side, this is 3 by r to the power 4 plus 4 pi r delta of r. Now what is this term? This should be multiplied by r cap to get g of r, and if we write instead of r cap r vector r by r, this is minus 3 r by r to the power 5 plus 4 pi vector r by r square delta of r. This is the term, this is the expression for, so I have written it wrongly. This should be written, please, sorry, this should be written over here, not right here. This is minus 3 r by r to the power 5 plus 4 pi vector r by r square delta of r. So the both the terms have been evaluated. So we can use these two to get the field due to a dipole. So to say, this is the value of g or grad of 1 by r for r not equal to 0, and this is the value at r is equal to 0. So if we write this, so E at r now comes out to be minus k times vector p by r cube p dot r times this term on rearranging we write it as in terms of unit vectors, unit position vector, this can be written as p dot r cap times r cap by r to the power 3 minus p by r cube, this is cube, minus 4 pi p dot r cap times r cap delta of r. This is the field expression for the electric field that is produced by the electric dipole. If we calculate field at points other than O, this is the expression of field. If we want to calculate field at O, this is the expression for the field together with K. Now let me justify the appearance of this term. So our aim is to find out the appearance of this term. Now we consider a dipole as this, and we want to find out the field at a point Q which is at a distance delta to the right of O. So at the point Q, if we place a test charge, positive test charge, minus Q pulls it in the direction of QA, and plus Q pulls it away in the direction BQ. So altogether both the forces are along B to A, that is along the negative P. And the magnitude of the force when a test charge is pressed at Q, it is KQ. This distance is this much is S, and this is delta, so 1 plus S plus delta whole square plus 1 upon this much is S minus delta whole square. So this is equal to KQ by S square minus delta square whole square, and in the numerator we have 4S delta. Now if we choose the value of delta very close to the midpoint, that is delta tends to 0. So as delta tends to 0, we can neglect delta square in presence of S in the denominator. Also this becomes KQ 4 S delta by S to the power 4, that is equal to OKQ delta by SQ. Now, if we for a dipole, what happens for a dipole? Okay, let me write it as this. Twice SQ is P, so this is K twice KP delta by S to the power 4. It is better to write in. For a point dipole, S goes to 0 and but P is finite. So this becomes infinity as S goes to 0, this tends to infinity, which justifies the affluence of this term, this singular term. This term becomes very important if we consider the dipole-dipole interaction. Say the dipole is one, this another dipole is this. So this there are two dipoles with common center. Then a potential term will arise from this part, and which is known as contact potential, that we shall discuss later. So this is the first lecture on dipole, electric dipole. In the second lecture we shall discuss what happens when an electric dipole is placed in an electric field. That will be the subject matter of the second lecture on dipole, electric dipole.